Hi, good day everyone. Today I am going to discuss the backtracking algorithm. The term backtrack was coined by American mathematician Derek H. Limmer in the 1950s, and Robert G. Walker was the first man who used the well-known deep-first procedure on backtracking in 1960. A backtracking algorithm is a problem-solving algorithm that has a brute-force approach in nature for finding the desired output. So based po on the previous report that a brute force is an algorithm na kung saan sinusubukan ang lahat ng mga posibilidad hanggang sa mahanap ang solusyon. So backtracking is an improvement of the brute force approach where it tries to search for a solution to a problem among all the available options, and it finds a solution set by developing a solution step by step in an increasing levels with time. And the term backtracking suggests that if the current solution is not suitable, then backtrack and try other solutions. Thus, recursion is used in this approach. So, in the backtracking algorithm, at each node, we try to eliminate the choices that are not possible and proceed further to recursively check only those choices that can contribute towards the solution. And also, the recursion is only done if the given problem only requires one solution. Otherwise, it continues searching for other possible solutions. In backtracking, solutions are represented in the form of a tree, and the tree is known as a state space tree. Since backtracking follows the DFS or the deep first search, the tree will be formed using DFS. So DFS is an algorithm for searching a graph or tree. The algorithm starts at the root node of a tree and goes as far as it can down to a given branch, then backtracks until it finds an explored path and then explores it for a possible solution. So this is the state space tree. So as we have observed, nakikita po natin ito sa ating machine learning kagaya po ng mga decision trees. So the state space tree is a tree that represents all the possible states of the problem, whether it is a solution or a not solution. And a node in a state space tree is said to be promising if it corresponds to a partially constructed solution that may still lead to a complete solution. Otherwise, it is called non-promising. So, ang part po na ito ay tinatawag non-promising since ang mga node po ay gumagawa po ng mga partially constructed solution, pero in the end, it is not a solution. But this one, the node created a partially constructed solution and it leads to a complete solution. Thus, it is called promising. This is the pseudocode for the backtracking algorithm. It gives a template of a generic backtracking algorithm. Input the elements of the REX from index 1 up to index I. Specify first I promising components of a solution where the first I promising component is equals to 0. Output all the tuples representing the problem solution. If the elements of the REX from index 1 up to index I is a solution, then we'll write REX from index 1 up to index 0, where it represents the empty node. Else, for each element x in the set Si plus 1, consistent with REX from index 1 up to index I, and the constraint, we will do x is equals to REX from index I plus 1, where index I plus 1 refers to the element in the REX that comes after the element at index I, and the value of x is assigned to this element, overwriting its previous value. Then, backtrack is a recursive call to the algorithm with the updated partial solution, which is the elements of the REX from 1 up to index I plus 1. Overall, the algorithm exhaustively searches the entire state space tree of possible solutions by trying all possible values for each element of the REX and backtracking when a dead end is reached. The algorithm terminates when a complete solution is found or when all possible combinations of values have been tried. Now, the first problem that we're going to solve using backtracking technique in the form of space 3 is the in-queens problem. The given problem statement is, given a chessboard of size n, the problem is to place in queens on the n times n chessboard, so no two queens are attacking each other. So for the in queens, we have four crossboards, means we have four rows and four columns, where the queens will be placed respectively in their position. So the aim of the in-queens problem using backtracking technique is to place the in-queens on their respective position without attacking each other. So in order to avoid two queens from attacking each other, there are bounding rules to be followed, such as the in-queens should not be in the same row, same column, and in diagonal position, because if they are in the same row, same column, or in diagonal position, then it will allow the queens to attack or to collide with each other. So it is very important that they should not be in the same row, column, and in diagonal position. Now we will solve the in-queens problem using backtracking technique in the form of state space 3. So the first I-promising component in the solution in our state space 3 is 0, and it is an empty node. So this is not yet the solution. So we will do x is equals to the elements of Rex I plus 1. So since our index I here is 0, so 0 plus 1, our x is equals to 1, wherein we will place the queen 1 in column 1, row 1. And then, since it is consistent with the constraint, then we will go to the next value. So our I here now is 1 because 1 is used to represent the index of the last element that has been assigned to a value in the array X. So our index I is 1, so 1 plus 1, X is equals to 2, where we will place the queen 2 in column 2, row 2, and we have observed that both the queen 1 and queen 2 are in diagonal position, thus they are attacking each other. And based on the bounding rules that there should be no two queens that are in diagonal position in order for them to avoid attacking each other. So this is not a solution. And right now what we're gonna do is to backtrack. And our I here is 2 because it is the last element that has been assigned to a value in the array X. So 2 plus 1, our X now is 3, wherein we will position the queen 2 in column 3, row 2. So there are no other queens that can attack queen 2. So we will continue. Our I is 3. So 3 plus 1. So our X now is equals to 4, wherein we will place the queen 3 in column 2, row 3. So the queen 2 and queen 3 are in diagonal position, thus they are attacking each other. So this is not a solution. Since it is not a solution, so we will backtrack, and then our I would be, since 4 is the last element being stored, so 4 plus 1, our X now is 5. So we will place the queen 3 in column 4, row 3. And again, both queen 2 and queen 3 are in diagonal position. And based on the bounding rules that there should be no two queens that are in diagonal position in order for them to avoid attacking each other. So therefore, this is not a solution. So in our 4 crossfolds, we'll remove queen 2 and queen 3. So in our state space 3, since it is a dead end, so we will backtrack. And the last element that has been assigned is 5. So it would be our index I. So 5 plus 1, X now is 6, wherein we will place the queen 2 in column 4, row 2. So since it is consistent with the constraint, then we will go to the next value. So 6 plus 1, our X now would be 7. And we will place the queen 3 in column 2, row 3. And then since there, there are no other queens that can attack queen 3, so we will continue. And then our index I now would be 7 since it is the last element that has been assigned in the REX. So 7 plus 1, our X now is 8. And then we will place queen 4 in column 3, row 4. So we have observed that both the queen 3 and queen 4 are in diagonal position, thus they are attacking each other. So this is not a solution, it would be a dead end. So in our four crossfolds, we will remove queen 3 and queen 4. And in our state space 3 is we're gonna do the backtracking. So the last element that has been stored in the REX is 8, and this will be our index I now. So 8 plus 1, so X now is equals to 9, wherein we will place the queen 3 in column 3, row 3. And again, we have observed that both the queen 2 and queen 3 are in diagonal position, thus they are attacking each other. And again, based on the bounding rules that there should be no two queens that are in diagonal position in order for them to avoid attacking each other. So therefore, this is not a solution. So since this is not yet a solution, so we will backtrack. So since we have tried all the positions and we haven't find the valid solution, so in our four crossfolds, we will remove the queen 1, queen 2, and queen 3. And in our state space 3 is we're gonna backtrack to the root node. And since 9 is the last element that is being assigned to a value in the array x, so 9 plus 1, so our x now is equals to 10, wherein we're gonna place the queen 1 in column 2, row 1. So since it is consistent with the constraint, then we will do so 10 plus 1, x is equals to 11. And then we will place the queen 2 in column 1, row 2. So we have observed that both the queen 1 and queen 2 are in diagonal position, thus they are attacking each other. So therefore, this is not a solution. So since 11 is the last element that has been assigned to a value in the REX, so this will be our index I now. So 11 plus 1, x would be equals to 12, wherein we will place the queen 2 in column 3, row 2. So we have observed that both the queen 1 and queen 2 are in diagonal position, thus they are attacking each other. So therefore, this is not a solution. So since we have reached the dead end, so now we will backtrack and then 12, which is the last element being assigned to a value in the array x. So 12 plus 1. So x now is equals to 13. And we will place the queen 2 in column 4, row 2. And since it is consistent with the constraint, then we will go to the next value. And 13, which will be our index I. So 13 plus 1. So we have 14 as x. So we will place queen 3 in column 1, row 3. So there are no other queens that can attack queen 3. So we will continue 14, which will be our index I. So 14 plus 1. So our x is equals to 15. So we will place queen 4 in column 3, row 4. So since the queens are in their respective positions without attacking each other, since there are no two queens that are in the same row, same column, or even in diagonal position, thus the solution is for the queen 1, it is column 2, row 1, and for the queen 2 is column 4, row 2, and for the queen 3 is column 1, row 3, and for the queen 4 is column 3, row 4. So we have observed that from the root node, that it tries all the possible solutions until it leads to a satisfactory solution of the given problem. And in the state space 3, this is the promising node since it constructs a partial solution and leads to a complete solution, while these nodes represent the non-promising since it constructs a partial solution, but in the end, if it is not a solution. And one of the games that uses the Ingrin's problem bonding rules is Sudoku. So Sudoku is a game being played by every individuals, and the game's rule is that the 9 by 9 square must be filled in with numbers from 1 to 9 with no repeated numbers in each line, whether horizontally or vertically. So just like the in-twins problem, there should be no in-twins that are in the same row or in the same column. Next is the Hamiltonian circuit problem using backtracking technique in the form of the state space tree. It is defined as a cycle that passes to all the vertices of graph exactly once, except the starting and ending vertices that is the same vertex. So ang ibig pong sabihin na ang cycle ng mga vertices sa graph ay dumadaan lamang po ng isang beses, maliban sa una at huling vertices. So over here is a graph that will be used to determine the Hamiltonian cycle. And it is said that if a graph has a Hamiltonian cycle, then the graph is said to be Hamiltonian. So to start with our search, we will select vertex A. And 0 is the first promising I component of the solution in our state space 3, with vertex A as the root of our state space 3. And then to break the three-way tie among the vertices adjacent to A, which are vertex B, C, and D, we will select vertex B. Because based on the lexicographical order or alphabetical order, B is next to A. And then now we will select vertex C, which is adjacent to B. And we will select vertex D, which is adjacent or next to C in alphabetical order. And then now we will select vertex E, which is adjacent to vertex D. And then we will select vertex F, adjacent to E, which is a dead end. Kaya po siya nagiging dead end kasi from vertex A, it will visit vertex B, and then from vertex B to vertex C to vertex D, D to E, and E to F. So nabivisit na already ang vertex B, and based po on the definition that the vertices will only pass through the graph only once. So kaya po hindi na po pwedeng i-visit ni vertex F si vertex B kasi vertex B po is already been visited by vertex A. So ngayon is magbabacktrack po tayo ng 3 levels up. So from vertex C, we will select vertex E. Kaya po hindi na po pwedeng i-select ni vertex C si vertex D kasi po na-visit na po niya si vertex D. So makikita po dito na from vertex C, it has been visited na po. Kaya hindi na siya pwedeng i-select. So now, the other option is to visit vertex E. So from vertex C, we will select vertex E, and then from vertex E, we will select vertex D, which is a dead end. Kaya po siya nagiging dead end kasi from vertex A to vertex B, and then to vertex C, to vertex A, and then to vertex D, kaya po siya nagiging dead end kasi hindi pa po siya pwedeng bumalik sa vertex A, which is the start and ending vertex. Kasi hindi pa po niya napapass through po lahat ng mga vertices na nasa graph, kaya po siya naging dead end. So now, we will backtrack 1 level up, and then from vertex E, we will select vertex F, and then dead end na naman siya kasi again, hindi niya pwedeng i-visit si vertex B kasi vertex B has been already visited and all the vertices need to be visited only once except the start and ending vertices. So now we will backtrack 3 levels up. So from vertex B, we will select vertex F, and from vertex F, we will select vertex E, and we will select next to vertex E is C,
and then we will select vertex D, and now we will select vertex A again, which is the start and ending vertices. So makikita po natin na from vertex A to vertex B, F, E, C, D, it goes back to vertex A. So based on the definition po, na-pass through po lahat ng mga vertices ang graph exactly once, except lang po sa start and ending vertices. So ang ating Hamiltonian circuit is A, B, F, E, C, D, A. So na-found out po natin ang Hamiltonian circuit. So this graph is known to be a Hamiltonian graph. And then the ending and the last vertices is of the same vertex, which is vertex A. And the vertices that pass the graph exactly once are vertex B, vertex F, vertex E, vertex C, and vertex D. So the one in yellow color is said to be the promising node kasi po nagko-construct po siya ng partial solution, and at the end it leads to a complete solution, while the red one is the non-promising nodes kasi po nagko-construct po siya ng partial solution, but in the end it is a dead end, or it is not solution to the state space 3. Last is the subset sum problem using the backtracking technique. It is to find a subset of a given set A containing A1 up to AN of n positive integers whose sum is equal to a given positive integer B. So it means na sa isang set po, hanapin po natin ang mga subset na kung saan ang kanilang sum is equivalent po sa ibinigay na positive integer B. And it is convenient to sort the set's elements in increasing order. So we will assume that A1 is less than A2, A2 is less than, so on and so forth. So it is important po na nakasort po ang mga set's elements in increasing order para po madali po nating mahanap ang mga subset na kung saan ang kanilang mga sum is equivalent to the given positive integer D. And it is assumed that A1 is less than A2. So, mas mababa po ang value ng element number 1 kaysa sa set element number 2. And then, going to the left of the node corresponds to the inclusion of set's element, while going to the right corresponds to its exclusion. So, ibig kong sabihin na going to the left of the node ay isasali po natin ang mga set's element. So, it is indicated by with. While going to the right po, ay hindi po natin isasali ang element, so it is written as without. So, ang element ay hindi natin i-add sa recent sum na nakuha mula sa pag-add sa elements sa given na set. So, over here, we have set A containing the set elements which are 3, 5, 6, and 7. And then D is given to be 15. So the set elements are being sorted in an increasing order. And what are we going to do now is we have to find the subset whose elements add up to 15. And the sum of the elements in those subsets should be 15. So we're going to start now finding the subset whose sum is 15. Using the state space 3. So we have 0 as our root node, and we should always remember that when we are going to the left side of the node means that we will include the set element, while going to the right side of the node means that we will exclude the set element. So now, since we are going to the left side of the node, we will include the set element number 1, which is 3. So 0 plus 3, the sum is 3, and then 3 plus 5, since 5 is the second element in the set. So 3 plus 5, the sum is 8. And 8 plus 6, the sum is 14. And 14 plus 7, since if we will continue the state space 3, so we are going to the left side of the node, means that we will include 7. So 14 plus 7, the sum is 21. And 21 is greater than 15, so this is not a solution. So now we will backtrack one level up. So we are going to the right side of the node. It means that we will exclude the set element. So 8 plus 0, the sum is 8. And we are going to the left side of the node. So it means we will include the element. So 8 plus 7, the sum is 15. And 15 is the sum that we are looking for. So this is the solution. And according to the backtracking that if it found the solution, it has the option whether to stop or continue searching for other possible solution. So for this, we will continue to search for the other possible solution. So now we will backtrack one level up. So since we are going to the right side of the node, so we'll not include the element. So 8 plus 0, so the sum is 8. So 8 is less than 15, thus this is not a solution. Now we will backtrack 3 levels up. So since we are going to the right side of the node, it means that we will not include the element. So 3 plus 0, the sum is 3. And then going to the left side of the node, 3 plus 6, the sum is 9. And then 9 plus 7, since if we will continue the state space 3 and going to the left, we will include the 7. So 9 plus 7, the sum is 16 and 16 is greater than 15. So therefore, this is not a solution. Now we will backtrack one level up and going to the right side of the node means we will not include the element. So 3 plus 0, the sum is 3 and then 3 plus 7, the sum is 10 and 10 is less than 15. So this is not a solution. Now we will backtrack 3 levels up. And then since we are going to the right side of the node, so it means that we will not include the element. So 0 plus 0, the sum is 0. So going to the left, so 0 plus 5, the sum is 5. And then 5 plus 6, the sum is 11. And 11 plus 7, the sum is 18. So 18 is greater than 15, thus this is not a solution. So we will backtrack one level up. 5 plus 0, since we are going to the right side of the node. 5 plus 0, the sum is 5. And then 5 plus 7, the sum is 12. And 12 is less than 15. So this is not a solution. And then going to the right side of the node, 0 plus 0, the sum is 0. So 0 plus 13, the sum is 13. Kaya po siya nagiging 13 kasi kung i-continue po natin ang state space 3 going to the left side, which means that we will include the set element, which are 6 plus 7. So 6 plus 7, their sum is 13. Kaya po siya nagiging 13. So 0 plus 13, the sum is 13. And 13 is less than 15, thus this is not a solution. The solution that we have found using the state space 3, that in the set, the subset, whose sum is equal to the given positive integer d, which is 15, are only 3, 5, and 7. Since 3 plus 5, the sum is 8, and 8 plus 7, the sum is 15. And we have observed that the state space 3 data structure shows that in the first level, it shows that it is for the first element in the set, and in the second level is the second element of the set, and in the third level is the third element in the set, and in the fourth level is the fourth element in the set. Now we are in the advantages of backtracking. First, backtracking has a brute force nature. Due to its reason, it can solve maximum problems. Since backtracking will try all the possible solutions to find a satisfactory solution to a given problem. Kaya po siya nagiging brute force in nature. So based on po sa ating na-discuss a while ago. And then, backtracking problems are very intuitive to code. So according to dictionary, intuitive means that it is easy to understand or operate without explicit instruction. And the step-by-step representation of the backtracking solution is straightforward to understand. Kaya po siya nagiging madaling intindihin kasi based po sa ating state space tree ay ipinapakita niya po kung paano nakukuha ang solusyon sa isang given na problem sa pamamagitan po ng pag-develop ng solutions step by step. And then, you can easily debug backtracking code. So if the backtracking has advantages, then it has also disadvantages. And those are, when compared to other options, it is quite slow. And depending on your data, it is possible to use backtracking to conduct a thorough search that ultimately yields no results that meet your search criteria. And backtracking is a recursive algorithm with a high computational cost that uses a lot of memory and the CPU. Last, due to the usage of recursion and stack storage for function information, there is a high space complexity. So the next algorithm that we're gonna discuss is the branch and bound algorithm. Branch and bound is one of the techniques used for problem solving. It is similar to the backtracking since it also uses the state space tree. It is used for solving the optimization problems and minimization problems. So the first problem that we're gonna solve is the assignment problem. It is assigning n people to n jobs so that the total cost of the assignment is as small as possible. An instance of the assignment problem is specified by an n times n cost matrix C so that we can state the problem. So over here, we have the cost matrix C with person A, B, C, and D, and job 1, job 2, job 3, and job 4. So to start, we shall find for the lower bound through determining the minimum job cost for every person. So among the four jobs, the minimum job cost for person A is 2, and for person B is 3, and for person C is 1, and for person D is 4. So the minimum job cost for every person shall serve as our lower bound. So 2 plus 3 plus 1 plus 4, the sum is 10. And it means that there should be no lower bound that is less than 10. And now we will start searching for the job that will be assigned for person A. So we'll start person A with job 1, and then we selected 9 for job 1 in person A since job 1 is not yet assigned to any person. And then since job 1 now is assigned to person A, so we will exclude job 1 from person B, C, and D. And from the remaining jobs of the person, the minimum job cost will be selected. So now the minimum job cost for person B is 3, and for person C is 1, and for person D is 4. And the sum is 17. And now we will try person B for job 2. So now we select 2 in the job 2 for person A since job 2 is not yet assigned to any person. And now since job 2 is assigned to person A, so we'll exclude job 2 from person B, C, and D. So now the minimum job cost for person B is 3, and for person C is 1, for person D is 4. The sum is 10. And then person A for job 3. So we selected 7 since job 3 is not yet assigned to any person. And now since job 3 is assigned to person A, so we will exclude job 3 from person B, C, and D. So 7, and then in the minimum job cost for person B is 4, and for person C is 5, and for person D is 4. The sum is 20. And then we will try person A for job 4. So we selected 8 since job 4 is not yet assigned to any person. And then since job 4 now is assigned to person A, so we'll exclude person B, C, and D from job 4. And now the minimum job cost for person B now is 3, and for person C is 1, and then for person D is 6, and the sum is 18. So as we can see over here that the smallest lower bound that we have is 10. So it means that the job 2 is for person A. So since job 2 is assigned to person A, we will exclude job 2 in the cost matrix C. Now we will continue searching for the assigned jobs on the remaining person, which are person B, C, and D. So for person B, we will try to assign job 1. So for person B, for job 1, we have 6 since job 1 now is not yet assigned to person C and D. So since job 1 now is assigned to person B, so we'll exclude job 1 from person C and D. So the minimum job cost for person C is 1, and then for person D is 4, and its sum is 13. And then job 3 for person B, so we have 3 as the minimum job cost, and then we will exclude job 3 from person C and D. So the minimum job cost now for person C is 5, and for person D is 4, and its sum is 14. And then person B for job 4, we have 7. And then we will exclude job 4 from person C and D. So the minimum job cost now for person C is 1, and for person D is 7. So 2 plus 7 plus 1 plus 7, the sum is 17. So among the lower bound that we have here, the smallest lower bound is 13. So it means that person B is assigned now to job 1. So now since job 1 is assigned to person B, so we'll exclude job 1 in our cost matrix C. And then we'll continue searching for the unassigned jobs, which are job 3 and job 4 with person C and D. So person C, for job 3, we had 1. So we'll exclude person D in job 3. So the minimum job cost for person D is 4. So the sum is 13. And then person C for job 4, we had 8. So we'll exclude person D in job 4. So the minimum job cost is 9. 2 plus 6 plus 8 plus 9, the sum is 25. So among the lower bound that we have here, the smallest lower bound is 13. So it means that person C is assigned to job 3. So we'll exclude job 3 in the cost matrix C since it is now assigned to person C. So the remaining job is job 4 with person D, which has no assigned job yet. So we could assume that job 4 is assigned to person D, but we will still continue to solve. So the minimum job cost for person D in job 4 is 4. So 2 plus 6 plus 1 plus 4, the lower bound is 13. So job 4 is assigned to person D. So now the assigned jobs for every person is person A is for job 2, and person B is for job 1, person C is for job 3, and person D is for job 4. Now we will apply the branch and bound algorithm to the knapsack problem. Given n items of the known weights Wi and values I is equals to 1, 2, up to n, and a knapsack of capacity capital W, find the most valuable subset of the items that fit in the knapsack. So just like in the subset sum problem using backtracking technique, in the knapsack problem, in the left branch indicates the inclusion of the items, while in the right branch is the exclusion of the items. And in order to find the most valuable subset of the items that fit in the knapsack, we shall use the formula for the upper bound, which is V is the total value of the items already selected and the product of the remaining capacity of the knapsack and the best unit payoff among the remaining items. So this V is the total value of the items that is already selected, and capital W is the knapsack's capacity, and this is the weight, and this is the value to weight ratio of the selected items next to it. Here we have the knapsack's problem, and the knapsack's capacity is 10, and we have the item 1 to 4 with their weight and value. So the value to weight ratio is 10 for the item 1 since 40 divided by 4. So the value to weight ratio is 10. And for the item 2, the value to weight ratio is 6. And for item 3 is 5. And for item 4 is 4. So here, as our starting or the root node, we have weight which is 0 and the value is 0. So the upper bound is 100. So we will start with 1. So as we have said a while ago that in the left side is the inclusion of the items. So we'll start with 1 and now we will solve for their upper bound. So with item 1, its weight is 4 and its value is 40. So to for the upper bound of the with item 1. So its value is 40 plus the knapsack's weight capacity is said to be 10 and then the weight is 4 for the item 1 and then the value to weight ratio next to the selected item is 6 since we selected item 1 so its value to weight ratio next to it is 6. So we have 40 plus 10 subtracted by 4, its difference is 6. And 6 multiplied by 6, its product is 36. So if we add 40 plus 36, their sum is 76. So now the upper bound for the with item 1 is 76. And then now since we are going to the right branch, which means the exclusion of the item, so the value is 0 and then the weight of the knapsack's capacity is 10 and then the weight is 0 and then the value to weight ratio next to the selected item is 6. So 0 plus 10 subtracted by 0, so the difference is 10, and then multiplied by 6, so their product is 60. 0 plus 60, the sum is 60. So the upper bound for the without 1 is 60. So as we can see over here that 76 is much higher than 60. So we will continue with this one. And then since we are going now to the left branch, as we can see that it is not feasible. The reason kaya po siya naging is not feasible kasi the knapsack's weight capacity lang po is only 10. So 11 is much higher than 10, kaya po siya hindi po pwede. The reason kaya po siya nagiging 11 kasi 4 plus 7, which is the with item 2, so 7 plus 4, its sum is 11. And then now we will try it without the item 2 since we are going to the right branch. So we'll just copy its weight and its value. So here the value is 40 and then the knapsack's capacity is 10 and then its weight is 4 and then the value to weight ratio next to the selected item for the item 2 is 5. So 40 plus 10 subtracted by 4, its difference is 6. 6 multiplied by 5, so their product is 30. So 40 plus 30, its sum is 70. So the upper bound for the without 2 is 70. So now since this is just the upper bound, the highest upper bound, so we will continue with this one. And now we will try it with 3, with item 3. So the weight now is 9 and then the value is 65. Kaya po siya nagiging 9 kasi 4 plus 5, the weight for the item 1 is 4 and then the item 3 weight is 5. So 4 plus 5, so the sum is 9 and then the value is 65 kasi 40 plus 25, so their sum is 65. So the said value is 65 for the with item 3 and then the knapsack's capacity is 10 and then its weight is 9 and then the value to weight ratio next to the selected item, since we select item 3, so ang next na value to weight ratio next to it is 4. So 65 plus 10 subtracted by 9, so we have 1 multiplied by 4, so we have 4 as the product. 65 plus 4, its sum is 69. So the upper bound that we have for the with item 3 is 69. And then we will continue with without 3 since we are going to the right side of the branch. So we will just copy the weight and the value. So the value is 40 plus the knapsack's capacity is 10 and then its weight is 4 and then the value to weight ratio next to the item is 4. So 40 plus 10 subtracted by 4, the difference is 6. 6 multiplied by 24, 6 multiplied by 4, their product is 24. So 40 plus 24, their sum is 64. So the upper bound for without 3 is 64. So as you can see over here that 69 is much higher than 64. So we will continue with this one. So if we are going to the left side, it means that the inclusion of the items. So if we will include item 4, its weight is 12. So it is not visible kasi again, the knapsack's weight capacity is only 10. And then 12 is exceeding 10. So it is not visible. Kaya po siya nagiging 12 kasi 9 plus 3, which is the weight for the item 4. So its sum is 12. And again, it is not visible kasi the knapsack's weight capacity is only 10. So, ngayon, pupunta po tayo sa right branch, which is the exclusion. So now, we will just copy the weight and the value. So, the value is 65 plus the knapsack's weight capacity is 10 minus the weight, which is 9. And then, since there are no value to weight ratio next to the selected item, so we'll just put 0. So 65 plus 10 minus 9, the difference is 1 multiplied by 0, so we have 0 as the product. So 65 plus 0, the sum is 65. So 65 will be the value. So this is the optimal solution since we just have 4 items. So the most valuable subset of the items that will fit in the knapsack are just only item 1 and 3. With the weight which is 9 and value is equals to 65. So as we can observe that 9 is less than 10 since the weight capacity of the knapsack is only 10. So pasok po siya. And its value is 65. So kaya po ang weight niya is only 9 kasi 4 plus 5 since we are the most valuable subset lang is item 1 and 3. So 4 plus 5, we have 9 and their value is 40 plus 25. So the sum is 65. The advantages of branch and bound algorithm. In terms of time complexity, the branch and bound algorithm does not explore all nodes in the tree. Thereby, the time complexity is significantly lesser than most other algorithms. And it has optimal solution. If the branching is done reasonably, the algorithm can find the optimal solution in a reasonable period. And it has a clear pattern since the branch and bound algorithm does not repeat the nodes to explore the tree for the candidate solutions. Instead, it follows a minimal path to derive the optimal solution. And if it has advantages, then it has also disadvantages. Since it is time consuming, based on the size of the problem, the number of nodes that are computed might be too large in a worst case scenario, making it a time consuming process. So that's all. Thank you for listening and God bless us all.